All right, Canvas homework 10.01 is about a suction cup, and it's 30 millimeter diameter suction cup. And you know how a suction cup works. You push it and then it springs back and it lowers the pressure inside the suction cup, between the suction cup and whatever it's pushing against. So we have something like this, a wall, and a suction cup kind of like that. Maybe it's got a hook on it or something. And you push it and it pulls back and it lowers the pressure here. So it lowers it to 63%, 0.63 times P. And out here the pressure is P. And of course the P that we mean is the atmospheric pressure. So we have atmospheric pressure out here. The suction cup lowers that to 0.63 times the atmospheric pressure. And what is the holding force, in quotes, between the suction cup and the wall? So I didn't get real detailed here. I expected you to probably come ask in office hours. But basically we're just asking, this pressure difference pushes on the suction cup. How hard does it push? And if you really want to think of a little further the mechanics, then you'd say, okay, well this suction cup is an object. And if we had to draw it as a free body diagram, this force due to the pressure difference would apply a force that way because the higher pressure outside pushes it, and the wall is going to apply a normal force back because it's not moving in this direction. And then what holds it up is, since there's a normal force between the suction cup and the wall, there's also static friction that keeps it from falling. Anyway, we didn't really want to get into all that with this problem. It was just a more straightforward question. What is the force pushing on the suction cup due to the difference in pressure? All right, so we can sort of idealize this suction cup as just a simple object with an area, right? You need to think about area to get a force or a pressure. And what you got to remember is that, let's see, the force is the pressure times the area in this sort of non-vector world that we're doing this in. Technically, this is a vector and A is a vector. But let's just think in terms of magnitudes and which ways you think of the forces as going. So you can get the force on this side due to the atmospheric pressure, and on this side due to the reduced atmospheric pressure, but really we need the net force. So we have two forces. We have the force from the left, and we have the force from the right. And I drew this one a little bigger because, as you can see, the force is the pressure times the area. The area is the diameter of this thing, it's circular, and there's the diameter. So you have a larger pressure pushing that way and a smaller pressure this way. So really then, if we just wanted to say sum of the forces in the x in this case, we have, and we'll call this the positive x direction, then we have the force left minus the force right, where I'm using positive and negative signs rather than vectors. So we say, okay, what's the force on the left? Well, it's 101,325 is atmospheric pressure in pascals in Newton per meter squared. And the area it's a circular diameter. I think the real problem said it was a circle, is pi times the radius squared. So half of 30 millimeters, 15 millimeters, turn it to meters, 0.015. Right? That's the atmospheric pressure, but we don't have a perfect vacuum on this side. There is some gas pushing that way. So we would say minus, and the force on the right is just 0.63 times atmospheric pressure. 0.63 times 101,325 times pi times 0.0. Right. The area is the same for the two. So you could really just say 1 minus 0.63 times all those numbers. And if you do all that, you get, I'm not going to do the algebra or the plugging in, 26.4 newtons. So in the fluid mechanics section, we eventually develop lots of equations that just depend on pressure. And we don't want you to think about forces. We want to just think in terms of pressure. That's what you do in fluid mechanics. But occasionally, we'll bring it back to forces just to check sort of a physical understanding. In this case, we assigned a problem like this because this was about how we were defining pressure. We want to make sure you think about the force you get. Well, that pressure is force per unit area, or you can turn it around and get the force from the pressure in the area, and that there are pressures on two sides of things. So that's all involved in this problem.